So I'm Eldridge. I'm working with Peck primarily, who's a conservation biologist. My background is in, let's say, evolutionary adaptive systems, kind of artificial life, computational biology. So I came across these ideas maybe 13 years ago and was looking at them looking at sound as a resource in evolutionary terms and looking at kind of agent-based models of these. And no one really took it that seriously maybe in ecology, and I've kept my eye on it and seen it become fashionable. So just in the last few years said, okay, let's see if we can apply these ideas to practically in the field. So Meek is a conservation biologist. He's concerned very simply and not unproblematically with preserving the rainforest in Ecuador. So we're working in Ecuador, particularly in an area where there's the last population of the brown-headed spider monkeys in the Choco forest in the western Amazon. So very grassroots, we need to keep this forest standing, we need to keep the species alive kind of work. Paola Moscoso is our PhD student. She did her undergraduate finding this area where the spider monkeys live. So we worked together, us three last year in the Amazon in Ecuador and in the cloud forest. Noe Morales is one of the owners and founders of the Santa Lucia Reserve where we worked. And I've just very recently, since Easter weekend actually, when I made this paper, I've been working with M.Casey, who's an English guy now working at Dartmouth University, and his background is kind of neuroscience, perception of audio, and digital representation of audio inspired by biological approaches. So it's his algorithms I'm looking at today. It's very, I've called it an ideation paper. We'd say hand-wavy. So there's no final results. It's saying maybe this would be interesting to look in this direction. So we will look, some of the context, a lot of this ground has been covered already, and in fact it brings together the ideas of Gianni from yesterday in Soundscape Ecology, some of the ideas of looking at time frequency representations, and then coming to get to the Amazon and South America. So I'll give a quick overview of the context, if you like. Very quickly, I'm just using some samples from our survey, so I'm not going to go into detail about our full survey, and then some quick illustrative results, let's say, of where we might go next. So we all know this, why are we wanting biodiversity? Well, we all care about the world, but now there's also money, because there's lots of multinational initiatives to preserve it. The RED, preserving forests, there's various UN initiatives for urban planning, and then the 80 biodiversity targets. And I think that's why we're all here. There's now grants to work in this area and to really try and make practical tools. So the big idea, if you like, which we all go, yeah, let's make some autonomous recorders and we'll leave them in the jungle and they'll just send us a floating point number once a week and we'll know how the forest is. Right, great, but it's hard. We all know that. So it's worth just taking a step back. Most people here, I think, are more maybe computer science, bioacoustics. Just think, well, what is biodiversity and how do ecologists measure it? Because many of these early community-level indices very sensibly are directly inspired by the way that ecologists work. So we all know biodiversity, well, it's a slippery concept, actually. It's not an SI unit. It's not like weight or length. It's not mass. It's relative. It's always relative. So it's something in part around the number of species encountered at a particular time, at a particular place, and how these change spatially across habitats, across time, and the turnover. So traditionally, ecologists put on their rubber boots and they go outside and they stand maybe for birds at 10 o'clock at dusk and at dawn. They have a pen and paper and they stand in a place and they say, what bird can I see, what bird can I hear, and how far away is it? Yeah, and we do this over and over again. And we all know that we need experts, it's very expensive, it's very time consuming, it's difficult to access these places. And then we tally the categories, and the categories may be species, but they may be genera, family, functional units, something higher up, right? And the abundance measure, again, is individuals, or it could be biomass or coverage if we're talking plants. And then we make a nice histogram. So this is from Santa Lucia where we're working. This is one primary forest site for 10 minutes on 5 consecutive mornings. So there's many different bird species here. We've been monitoring this place for about 5 years now on about 250 points. So we have a pretty good idea of the species that are there and how they change across habitat, and also altitudinal is the big variation, is the big gradient. But the crucial thing here, we have a count of species, abundance, and then we do some maths to try and boil this down to a number, right? That's what we always want, a nice number that summarises things. Some kind of diversity indices, and again in ecology, amongst ecologists, this isn't clear. This is an ongoing problem. Since the 50s, people argue which is the best one. The simplest is to say richness. How many categories are there in our histogram? Some kind of dominance measure, where what's the abundance of the category with the largest proportion? This gives us some kind of skew. A Gini-Simpson, these are all probably familiar to you all there. Some kind of measure of variance in the abundances. And the favourite one, Shannon entropy. And this is not terribly intuitive perhaps, but it's very popular. So we do entropy on the abundances, and the idea is that everything is equal, right? Maximum information is when we have a flat distribution. So the idea is that if we have 200 of one species and 1 of the other, that's different if we have an even amount. But it doesn't actually make, I mean, I'm not an ecologist, but it doesn't make that much sense. We might have 1 golden eagle and 500 tanagers. That doesn't mean it's the system is out of order, right? This flat distribution actually isn't very, very common. So that's difficult. Standing in the field with your boots is difficult. We all know why remote sensing is attractive. My colleague Mika has done a lot of work with visual remote sensing and shown that yes, you can do estimation of species from the canopy, but these areas, there's pollution, there's hunting, you have silent forests. So you can see the tree distribution of trees, but maybe there's no animals living underneath. So this is why we find the framework of soundscape ecology very appealing. This kind of modernises, if you like, brings together communication theory. So rather than there being channel, message, receiver, we're looking at this holistic system, bringing together landscape ecology, so understanding the dynamics of ecology at a large scale. And sound, if you like, is the interface. Sound is everything affects and creates the sound, and we can listen to the sound to try and understand the patterns of interaction between the humans, the animals, the landscape, etc. And the related idea is that all the animals in a community at a certain place that vocalise will create an acoustic community. Right? So this whole idea that we're not trying to necessarily ID certain species, but by listening to the global soundscape, we can maybe learn something about the dynamics of this acoustic community. And it's fair to say that the creatures that vocalise, birds, insects, we're not looking at bats, but bats are really good indicators, and the anurans, the frogs, are good indicators generally. There's lots of studies to show that these are good indicators of the health of the habitat. So moving on from the idea of soundscape, which was laid out by Brian Pishanowski, following on from work of Stuart Gage, etc., we start to separate out the components of a soundscape. Again, Pavan mentioned this yesterday. So there's anthrophony, low frequency, biophony, higher frequency, and the geophony, the sound of the wind and the rain as it is impacted in the landscape as well. The final key player, who talked about these ideas in the 90s, a guy called Bernie Krause, who may be familiar to lots of you. He was a musician, in fact, retrained as a bioacoustician and then spent thousands of hours in the field recording. And he put forward this idea of the acoustic niche hypothesis, say that the dawn chorus isn't a cacophony, that animals adapt their calls through spectro-temporal partitioning. Animals will find a unique space. So basically saying sound is a resource. Sound is a limited resource in the same way as habitat is, as food is, as mates are. So within niche theory, we expect through evolution, through competition, that animals will separate and try not to avoid having overlapping niches. And this is the basic idea, right? That very crudely put, he went so far as to say that this effect is so strong, this partitioning will structure the global soundscape to the extent that by listening to the global signature, we can infer the health of the habitat. He suggested this idea. So very, very crudely put, that in a healthy, stable ecosystem, you'll get this rich diversity of voices. The full spectrum, if you like, will be filled, but non-overlapping. So complex non-overlapping signals. Again, crudely put, if you go and fell over the trees, there'll be a gap. as the secondary invasive species take over, there'll be maybe competition, etc., etc. It's maybe not this simple, but there's lots of evolutionary, it's tenable in evolutionary terms, this idea, but we haven't yet got the tools to really investigate, actually what are the dimensions of the acoustic niche. So in some places we see, so this is a frog chorus in, sorry, oh, it's quieter. This is the frog chorus down in the Amazon basin, and yeah, actually, we get these like incredibly clear bands. But it's not always this way, right? Especially with the birds, we get these much, much more complex. So how can we begin to measure the dynamics of the acoustic community from a digital sound file? This is our problem, right? So there's been a whole bunch of acoustic indices that have been proposed. The very simplest ones for large-scale monitoring, actually, if we want to look, for example, at changes in onset of the dawn chorus according to weather patterns, or maybe with the structure of the landscape, or something like this, then even just looking at the RMS of a signal can be quite powerful. And this has been shown to reveal spectro-temporal patterns in a tropical forest. The normalised difference sound index is saying, looking at this anthrophony to biophony ratio, so just saying what's the magnitude below 2K and what's above. And again, over long term, so I think this study that they reported maybe over 4 years in some very distinct habitats. And you can see, yeah, this diurnal and annual variation in these large-scale kind of gross differences. Moving on, there's lots of, not surprisingly, taking their cues from ecologists, there's lots of spectral entropy measures. So looking at, essentially taking the spectrogram, looking at the proportion of signals, the magnitude of signals in each bin, and then calculating either the Shannon or the Gini to give us a diversity or evenness index. In the Minerva's one, they split the spectrogram into 10 bins and look at it like this. And again, this shows in long-term studies we can actually see the dynamics nicely coming out. But there's not so much local, it doesn't give us any local diversity. Jerome Sawyer, your supervisor, has also the acoustic entropy. So he does a similar thing in the time domain and the spectral domain. So a spectrogram, an entropy on the relative magnitudes, and then the time domain, Hilbert transform, looking at the entropy on the time wave envelopes, and then multiplies those together to give us H, this idea of overall acoustic entropy. We've had some, obviously this is sensitive to noise, right? Because white noise by a motorway, pure white noise, or maybe a cicada is broadband noise. So this will give us a maximum value, which is not really very intuitive. It maximises when we've got this actually not very complex sound. So Pieretti looked at this idea of acoustic complexity index, and this is essentially looking again in a spectrogram, looking at adjacent bins and seeing how does this change. How do the magnitudes of each frequency bin change across frequencies and across time? So the idea here, this is based on, anthrophony, aeroplanes and motors are fairly consistent. Birds change. As we see, birds have transients. Things change quickly over time. So let's look at, this is giving us some idea of change. This is very, very sensitive to the window over which we look at it as well. And then finally, quite a simple one, which was reported to be very powerful, but I'm particularly interested to look at in a larger scale study, is the bioacoustic index of Bowman. So this is literally mean spectrum and then minus the value of the lowest bin. So spectrogram, take the lowest bin, take that away, the area under the curve. So it gives us some measure of spread and an overall amplitude, overall power, if you like, in a signal. So these results are quite promising in terms of large-scale studies. We can start to automatically look at long-term spatio-temporal dynamics, over scales of a year, say. But in terms of local diversity, it's more challenging. There's lots of open questions. Many of these are very sensitive to environmental noise, to the distance from the microphone, and this approach of having a grid so that we can see, we haven't caught it on this one. So instead of having non-overlapping signals, we make sure we pick it up on two, and we can imagine can go some way towards it. And just the relative intensity, so the screaming peer is super loud bird, right? Other birds are crucially important, but very, very quiet. Like, we need to observe all of them. And more importantly, theoretically. So actually, even if we see some kind of correlation between sort of assumed changes in diversity, really, what aspect of compositional diversity are these capturing? And there was a paper, I think, that Glotin, you wrote with Lucia recently, where you were looking at temporal, some temporal changes, and it was shown that the indices were shown to, there was a MCC type, mel frequency type index, and it was shown that with simulated communities, so get a bunch of recordings, overdub them, let's control it manually, it reflected very nicely, it correlated very well. As you increase the number of species, you got a nice straight correlation. But in the wild, actually, this wasn't so easy. So we have to start asking what really are we capturing with these, and maybe we're missing something. My concern here is that if we, or certainly I, am interested in this community-level approach to the global soundscape and trying to understand the community-level dynamics, if we are assuming, which is the core premise of this approach, that the soundscape is structured dynamically through spectro-temporal partitioning, i.e. turn-taking, and species co-evolving and avoiding each other's, keeping off each other's territory, if you like, in the acoustic domain, then all of these indices are effectively 1D vectors. We're splitting the sound into either the frequency domain or the time domain, doing some fairly simple stats on them. So they're inherently insensitive to these 2D dynamics. So that was sort of what I was interested in. So are there some other techniques that we can steal from, or borrow, let's say, redeploy from other areas that allow us to start looking at these more dynamic patterns? So what I've looked at in this paper is shift invariant probabilistic latent component analysis. So effectively it's non-negative matrix factorization, but probabilistic and shift invariant. So it's unsupervised. We give it a spectrogram, we give it a 2D signal, and the problem is to estimate the kernels, the marginals, basically. So here we decompose non-negative matrix into the product of two distributions, and we're estimating these distributions in an unsupervised way. The parameters are computed using an EM algorithm, which Smaragis and Raj reported in 2007, 2008. From the basic PLCA, they demonstrate with some constraints how we can make this shift invariant, so we can look for patterns that shift in time or in space, in frequency or in timbre space as well. And this has been shown in lots of music information retrieval works. So for example, the first time I heard it or saw it in action was for a Madonna track, and you can pull out the vocal part, the drums, the keyboard, right? So basically it's saying where are the patterns, where are patterns in sound with statistics in time and frequency that move together, that have a shared statistical distribution. And depending on what we feed it, we can say, are these invariant to frequency, to pitch shifts, or to spectral shifts? So this has been used, Juan Bello in New York has looked at using this with to do automatic segmentation. We gave it all of the Beatles tracks, a chromogram of the Beatles tracks, and it will automatically chop up into verse, chorus, verse sections. If you set the priors, so Z, these prior distribution, you can impose a sparsity constraint such that the number of components returned is automatically pruned. So instead of like a PCA, where it gives you back a set of eigenvectors and you have to choose with some heuristic, I'll pick the first 3 when they're over this, when they've added to 1, this will automatically return a number which is, the X most relevant. I'm going to skip through really quick. Just to make this concrete then, if we give it a spectrogram, so this is a constant Q transform with some piano notes, right? So maybe jong, bong, 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 bong. So interleaved, 2 notes, 1 note, 2 notes, 1 note, 3 notes. It will then pull out a kernel distribution of the spectral characteristics, right? On a piano, the notes have the same spectral, a harmonic spectral outline, the fundamental, and then a space-time, so time and frequency. Then, so this is where this kernel sits in space and time. The first note, second note, etc. Yeah, and if we then convolve those two back together, we get an approximation, which is not only really true, but actually begins to sharpen the original signal. So this is with one kernel, but we can start to look for different kernels in different areas as well. I'm going to skip through these next bits. So I did some quick comparisons with other 2D dictionary approximations, which are in the paper, and the code's available on GitHub if you want. It's one of the Bregman toolkits. So there's some Python notebooks that you can go and have a play with. But really quickly, just to show, this is mini-batch gradient descent. This is the original signal, the approximation. Gabor field, 2D atoms approximation, and this is making a dictionary with 2D PLCA. So pretty good approximation, and I'm going to skip through why I think that works. Really quickly then, up in Ecuador, so here's all our wildlife acoustics recorders. It's a nature reserve, a forest site up, maybe 1 kilometre up in the cloud forest, with mixed terrain. So it's cloud forest, it's a mix of mostly primary forest. It's owned by 12 families that were fruit farmers. So 17 years ago it became a reserve, and they had to stop farming. So the secondary forest is what was there. They're fruit orchards that's now regrown. And to feed the donkeys, the mules, here there are various paddocks of elephant grass. So that's our silver pasture. So we did 3 weeks up here and 3 weeks in the Amazon basin, looking across these habitat types. This was actually Nenke down in the lowlands, and this is one of the trees up in the cloud forest where we were. So very basic 3 different habitat types, 3 replicates over 3 weeks in two different sites. I'm not even going to, sorry, I'm running out of time, so I won't go into the details of this. We did microhabitat, so our choice of habitats came from talking to the people there. You know, where's the primary forest, where was the orchard, etc., etc. But we did habitat assessments as well, obviously, to check if that was real. And then so this is Noe, Arise and Mika, who I work with. Noe has lived there since he was a boy. He knows and can sing every single species there. So he did point counts for us every morning at dawn. This is actually not a point, this is at my bedroom window. There's many of these tanagers here. So every morning for 10 minutes at each sites on rotation, Noe did a seen and a heard species and a distance count on the sites where we had our recorders. So just to look very quickly at just three sites. Am I right? Sorry, we're running, it's coffee time, yeah? So just done a sample analysis of just 3 sites, and all of this obviously needs to be done on a much larger scale to make any conclusions. So this is 10 minutes. He went round a primary site, the secondary site, the silver pasture site. They're maybe 300 metres apart, but actually they're on along a ridge. So there's some birds like the pier. There's a big cock of the rock there, and many of the guans that Vincent mentioned as well. And these birds you can hear a long way. So some of these appear on each site. Maybe it's the same bird that you can hear in the valley. Some of them just because there's a lot of shared species. So these are the species, these are heard, and this is seen. This was actually in abundance, but there's just one sighting for each one. So this gives us presence, absence, and abundance. So if we add them all up, you probably can't see these, but primary, secondary, silver pasture, actually in total, 25 species altogether in the silver pasture, 20 altogether in the secondary, and 21 altogether in the primary. So not really any differences in the number of species. In terms of the herd species, the silver pasture is actually the most herd, but these are very small differences. We're not going to make any conclusions. The key thing is that there's a lot of shared species. There are some kind of landmark, soundmark species, if you like, that are distinctive. As I say, we've done a 5-year survey of this, and so we know there are indicator species for each habitat, even though there's these complex and very subtle differences between the habitats. If I... maybe it's easiest to see. Oh, sorry, it's I'll just play some. Not a nice screen resolution, sorry. I'll just leave these playing while I carry on talking. So these are spectrograms just of 1 minute, but essentially the pattern's the same over 10 minutes. Very, very similar. And we saw that there's a lot of common shared species. The overall actual ranges of frequencies represented do not differ very much. If we look at the mean spectrum, we can see this. So green is the primary, blue is the secondary, red is the silver pasture. This is the constant Q, because I wanted to look at some of the lower frequency, but maybe arguably not the best transform. But the point is, it's largely similar, and we see slightly shifted peaks according to the dominance of certain species, right? So we see this sort of same pattern in the observations, the human observations, and this very global pattern. It's unfair maybe to test the acoustic indices on this. The differences are very, very subtle, very subtle. So if we run up the indices I mentioned, are all easily calculable in R. So the normalised difference sound index, maximum 1. No surprise, there is no anthrophony. We're in the rainforest. Acoustic diversity index. So again, this is looking at an entropy of spectrogram divided into 10 bins. Very similar in each. In fact, all the entropic measures are very similar and approach 1. That's no surprise. Each system is fairly constant. Acoustic complexity index, I actually am not going to say much about. It's very high across all, and it needs much more investigation because it's sensitive to the window analysis time. So if we look, the biodiversity index is essentially the area. So what we do is look at the lowest value and take that away, and so it's the area under here. So as we see here, secondary is the largest, primary second, silver pasture lowest, which is exactly what we see, secondary, primary, silver pasture. And this is our observations of herd for each one. So the most in the silver pasture, secondary. So this is one single sample. I'm not going to draw any conclusions from this, but just to say that these low-level differences are hard for these kind of broad brush indices to pick up, because what is characteristic, we could say, actually is not the frequencies represented. It's the patterns of interaction between them, right? It's the many of these even have the same species. There's tanagers in each one. There's Andean solitaires in each one. But it's the patterns of interaction between them that are really characteristic and really define what the behaviours and the characteristics of each site. So having a quick look with a PLCA, because this is giving it the 10-minute sample, so exactly the same 10 minutes that NOAA IJ the species for. Obviously we don't analyse the whole thing, it's computationally expensive, so we take 16 4-second samples and then splice them back together in time. So it's a fairly crude sampling method. So these are the original, the primary and secondary silver pasture, and these are the approximations. So just eyeballing them, it looks pretty convincing. If we look at some of the components as they come out, so what this gives us, remember, is the time frequency kernels and then the activation functions. And here, what we're looking for, it's in 2D. So it's like a SPLC 2D. We've got frequency, local time, and shift time and shift frequency activations. So these kernels convolve with these activation functions to give us the individual component constructions, and then put these together, we get an approximation. So we start to see with each one, we get these different patterns pulled out. We get some broader background noise, and then some more distinct, both in frequency range and in the patterns that are pulled out. For each one, we get a qualitatively different set out. So the primary forest. The secondary, as I mentioned, you can set sparsity constraints on the prior that you're modelling, which is the Dirichlet prior, and that automatically prunes. So here we get k equals 16, the maximum of components is 16, and it's returning 4. So in the secondary, we're getting 7 back, and again we get a mix of quite unique, like rhythmic, some broad band, some quite narrow band patterns. And in the silver pasture, perhaps we can see this best if I zoom in, sorry, they're a little bit small. So these are the individual component reconstructions for the silver pasture. If we look on the original, and it comes back to your question actually about sound propagation, in the silver pasture, right, it's very open, and we're on the side of a ridge. So actually there's much more background noise. It's the same day, it's the same morning, but because there's less trees, there's less attenuation, it's actually the overall ambient noise is higher, and that's our first component that comes out. Maybe, I don't know, this is one run, I'm wildly speculating here, but we get this first component out, and then we get these shifted from this actually a pattern, but quite mixed in terms of frequency range, we get these distinct banded patterns pulled out. What's quite interesting is, as well, I mean, it's computationally expensive. This isn't like a quick and dirty measure, but actually, if we start looking, even these time frequency kernels. So this is 1, 2, 3, 4, length of 8, right? These are actually, again, this is just eyeballing, but these look like pretty faithful lower dimension representations of the final component. Right? This seems to capture the same key ideas, this one isolated, so this is giving us an oriented, as we would do in a gabor, in a 2D atom, oriented in frequency and time, but also instead of whilst in a 2D, in a gabor atom you've got, we think of it as a filter, you can kind of stretch the filter width a little bit. Here we have a way to represent a big variety, either a very isolated event or some broadband noise. And finally, what I haven't shown here, but in the paper, that each of these components is described by a set of entropies, which then describe, the overall structure. So maybe, and this is really hand-wavy, maybe those are quite useful ways to summarise the components that are pulled out. So some of the questions, I said there can be no answers because we've just looked at one example for each one, but we know this algorithm works well in musical situations. M.Casey recently did a study where he was looking at groove. Yeah, so like we all know, our bodies all know what groove is, but it's actually quite a tenuous concept in terms of machine listening. What's our feature for groove? Where do we look at it? So running exactly this algorithm, we can, because it can find patterns that are invariant, not just to time shift, but time stretch and pitch shift and spectral shift, right? We can, whether we have a shaky egg pattern or a hi-hat, a ride pattern, we can pick up this pattern. So he showed automatic groove similarity measures and human judgments of groove similarity to perform well together, effectively. So we know this algorithm works well in the musical domain, and it strikes me, even though I'm not a biologist, I put my hands up and say I'm let's say a musician and system scientist, if anything. But from a summer in the Amazon last summer, this is what seems unique in different habitats: is the interrelationships between the birds. Yeah, it's not presence absence of a species. It's how do those species adapt to each other over time and in those particular spaces. And I just feel that these traditional, it's only 6 years old, but these 1D vectors, it's throwing away too much information. We need necessarily, with any metric, to simplify, but it feels very sensible to simplify in a 2D space, and ideally in a 2D space that's shift invariant. Yeah, because the call patterns of birds are periodic, but they're quasi-periodic, right? They're stretchy. So this is what I want to look at next: is are these component reconstructions meaningful? Are there objects extracted? Are these meaningful in any interesting ecological way? There's two levels. One, the acoustic community. Can we begin to understand and pick apart the individuals, how they contribute to the acoustic community? Maybe some sense of acoustic functional diversity, like we have functional diversity within species. But even looking, again, within the soundscape framework, say wind and rain, unless it's wind in our microphone, wind in the environment isn't noise that we're trying to clean off our recordings. We're interested in how this interacts with the birds, right? The anthrophony and the biophony interaction is exactly what we want to study. And at the moment, we don't really have any tools to begin to understand these dynamic temporal patterns. So maybe by pulling out and separating these components, we don't necessarily want the first component to be the screaming fear and the second one to be the wattled guan. We're interested in is it meaningful? What does it mean that primary had 4 components whilst another one had 7 components? Does the number of components returned suggest is it a measure of decomposability in some way? Is that related to complexity? You know, if it's a messy structure, would that be more or less easy to decompose? I don't know, but they seem like interesting questions. And I haven't even begun to look at what these entropic summaries. So just the same way as we've looked at an entropic summary of the relative magnitude in a spectrum, these are entropy summaries of these return components. So might these be a useful way of measuring diversity either within or between communities? Because we're ultimately interested in the soundscape as a way of monitoring habitat status. So is the habitat declining or improving? So yeah, very, very hand-wavy, very speculative, no solid results at all, but maybe an interesting new tool to be able to look at this in dynamically, to look at these patterns dynamically. And in particular for me, I feel like the idea of an acoustic niche is sensible. It makes sense, right? But we haven't yet got any tools to really understand, in terms of ecospace, in terms of evolutionary ecospace, actually what are the dimensions of the acoustic niche. It's not just what frequency band am I in, you know, it's something more complex and more adaptive. So maybe this is a useful tool to begin to start to study these. Yes, sorry to run into coffee break. Are there any questions?
Thank you.
Thank you.
Well, if you don't mind, maybe questions.
Yeah, questions in coffee or in coffee.
In coffee.
Yeah.
Yes.
And importantly, if anyone needs a job, I've got only 6 months of money, but to come and work on this when we get back. So we're going out to Ecuador this summer. We're doing temperate surveys on much more different, much broader gradient of primary, secondary, and silvopasture. We're going back to Ecuador again, and then I really want someone to work with because I'm working by myself at the moment. So I've got some money. But if you, or any of your students, or any of your colleagues or friends are interested in machine learning, particularly on exactly this, so working with M.Casey looking at this kind of stuff, please talk to me. Thank you.